Hello, hello. I'm back for paper 3. Because I'm gonna save paper 2 for last. I just don't like paper 2 questions because of all the calculator functions you need to memorize and stuff like that. Whereas paper 3, although you do have calculators, overall, I think most of the questions you generally don't need them. So there's like, what, 2 long-ish questions, and paper 3 is normally kind of easy because it's so broken down for you. Like, look, this goes to like HIII, that it's very guided. And I've never met a student that said paper 3 was hard. And I don't think that this one will be either. Okay, but excuse the writing. This just came with the scans that I got from my sources. But let's see what this is about. Okay. In a new computer game, each time a player performs an action, there is a random chance that this action will be boosted, meaning it provides you. Is this IV's way of trying to be like relatable? The designer of this computer game is considering 2 possible models for when to boost an action. In the first model, the probability that an action will be boosted is constant. Suppose that the probability of an action will be boosted is 0.1. Find the probability that the first boost occurs in the third action. Okay, so then that means that the first action is unboosted. So is the second action. So these are independent events. We can just multiply their probabilities together. And then the third one is the boost, right? So probably something like this. And then we can... I don't want to multiply it out, but there you go. That is question A. I. And then II. Find the probability that at least one boost occurs in the first 6 actions. So, like, let's say, like, let's say X is the number of boosts. Then we are finding the probability that X is at least 1. And because these are repeated events that are independent and it's the same event, this is a binomial distribution. Where n is 6. And, well, cumulative too, because we are looking for at least 1, right? So what you can do is you need a calculator. And I don't know if I still have my TI emulator. But let's see. Okay. And it's been a while since I've done this. But I think it's, if you have a TI-84, you go into the distribution menu. And then we go to binomial CDF. And then we have 6 trials. We have a p-value of 0.1. And then our x value... Okay, here's the thing about... I think a TI-84 plus Silver Edition is... They do lower boundary ones. So what I should be doing is... I should be rewriting at least 1 into a probability statement that has a upper boundary. So having at least 1, well, that's really thick. Having at least 1 is the same as finding the complement, which is having less than 1. Less than 1. And having less than 1 is the same as having none. So maybe I don't need a binomial cumulative distribution. Why don't I just go back? Get me out of here. And then we're just going to do 1 minus the probability distribution of getting no, whatever these are, boosts. Look at IB, trying to be so relevant and relatable to you guys. Okay. So, the probability of having at least 1 in 6 actions, 0.458 or whatever it said. Oh, 468. And then I guess you would round it to 9. Look, 69 even too. And look at this, sigma. they're trying to be so relatable. Okay, what's next? Suppose that the probability that an action is boosted is p. Explain why the probability that the first boost occurs in the X'd action is this. Okay, well, why do you need to explain it? Okay. I don't know how they want you to explain it. It's only worth 1 mark, but the probability of no boost is 1 minus p, right? And then X action means that you have X minus 1 unboosted actions. So that's why this has an exponent. And then of course on the final action, you hit the boost. So then this gets multiplied by 0.1 or p or whatever value this is. Okay, next, X is the number of actions until the first boost. Write an expression in sigma notation for the expected value in terms of X and P. Okay, I think I need more room. Okay, I need to move all of this stuff down. Okay, I can't move it down. Can I? Okay, let me just add some enters. And then this is only 1 mark, right? Okay, well, we can write a quick little distribution table. And it looks something like this. So X represents the number of actions, right? So like you can have 1 action, 2 action, 3 actions, 4 actions, and so on. And then, well, the probability that you get boosted in the first action is, we're gonna use this here. And then you could just say P, but I'm just gonna write it all out. And then this one is P 1 minus P squared, or sorry, to the power of 1. And so on. And if you want to calculate expected value, if you have this table, then you just take X and multiply it with P and then sum these up. And because this is an infinite thing, it could go on forever. It depends on, I don't know, how many actions you perform in the game, which is theoretically an infinite one. That's why they ask you for sigma notation. So this is from X equals 1 to, I guess, infinity. And then it's just X times... Oh, I guess I didn't need to fill out the table, but it helps you guys see what's happening, right? we just multiply these two together and then sum them up like this. And then consider for an infinite geometric sequence like this. This is the summation formula. By differentiating both sides in the above equation with respect to r, find an expression for this in terms of a and r. Okay, so I guess we'll take the derivative. And then on the left side, we're gonna get a plus 2ar plus 3ar squared. And then I'll just do one more. A r3 dot 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 equals, and then I take the derivative of the other side, so this is like negative a over 1 minus r squared. Okay, and then using this, they say find an expression for this infinite sum. And then if you notice, this infinite sum is literally this right here, right? It goes from n is 1, so 1, 2, 3, 4, 5. The exponent for r is n minus 1, so you can see here that's 1, 2, 3, and then there's even an a. Okay, so that means that this sum is this expression on the right. Okay. Hence, show that the expected value is 1 minus 1 over p. Wait. So we're gonna use this, right? It says hence to show this expected value here. Oh yeah, okay, so if you notice this expression, this summation matches with this, where of course this is, why is that so thick? Where instead we have x is n, p is a, and then 1 minus p is r. So I know that if I use this expression here, this is gonna be negative p over 1 minus 1 plus p squared. And then the ones cancel, so we'll have negative p over p squared, which is equal to negative 1 over p. Why is it negative? Did I mess up a sign somewhere? Okay. I almost have it. Did I mess up a sign? Wait, hold on. Okay. NAR, right? A is P, so P goes up here. And it's 1 minus R. Oh. I messed up the derivative of this. I forgot. Okay, there's a negative 1 from the exponent rule, and then there's another negative 1 from the chain rule, because there's a minus r on the inside. So this is positive, and this is positive, and then this is positive. Okay, done. Nice. So we have shown the expected value is 1 over p. And then, let's see, it can be shown the variance is 1 minus p over p squared. Find the expected value and variance when p is 0.1. Okay, so then we just plug these in, right? Expected value is 1 over 0.1, which is 10. And then the variance is 1 minus 0.1 over 0.1 squared, which is like 90? Where's my calculator? Yeah, 90. So I guess in terms of like interpreting this, you can expect 10 actions before you get a boost, and then there's a variance of 90. Okay, in the designer's second model, the initial probability is boosted 0.2, and then each time an action occurs that's not boosted, the probability is increased. Wow, by 0.2. After an action has been boosted, then the probability resets for the next one. Sheesh. That's actually a... well, I don't know if... like, if this is a gacha roll, that's some crazy... that's some crazy probability design. Show that the probability that the first boost occurs in the third action is this. Okay. So we have the first action, which has an 80% chance of not being boosted. Then the second event, the probability goes up to 0.4 for being boosted, so that means that it's a 0.6% chance or 0.6 probability of still being unboosted. And then finally, for the third one, each time you get 0.2, right? Yeah. So then by the third one, you have 0.6 chance of being boosted. And then if you multiply those out, you probably get 0.288. Let's see. Gut check. Yeah. Explain why... okay, why... let y be the number of actions until the first boost occurs. Explain why y is less than or equal to 5. Okay, so after 5 boosts, right? Because you're adding 0.2 every time, like this is 1 mark, but let me just explain it. Then by 5, right? By 5, then the boost probability is 1. So it's guaranteed to happen. So you're guaranteed to be boosted at least every 5 turns. Okay, the following table shows this probability distribution. Find the value of m and n. Okay, that's very standard. Basically, we know that the sum of these probabilities is 1. Actually, do I even need to do that? I don't even think I need to do this. Like, you can just calculate each of these separately, right? Because, like, usually, like, in this type of setup, they give you 2 variables because they also tell you what the value of the expected is, and then you make a system. But, like, you can just calculate this out, can't you? Am I going crazy? Like, m is the probability that you get boosted on the second, right? So then this is 0.6 times 0.4. And then n is you get boosted on the 4th. So that's 0.6, 0.8 is the probability of being unboosted. 0.6, 0.4, and then 0.8. Right? Unboosted and then boosted, unboosted, 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 boosted. Okay, yeah, let's just do it that way. It's only worth 2 marks. So this is 0.32? And then I don't want to do the other one in my head. But let me just double check that this one I did right in my head. Okay. So 0.8 times 0.6 times 0.4 times 0.8, 1536. Okay. And you don't have to do this. I'm going to do a gut check and add all of these probabilities together and see if it does sum to 1. Sick. Okay, there you go. Next, show that EY is this. Okay. Because we filled out the table, then you just calculate the expected value of y. So then that's just like 1 times 0.2 plus 2 times 0.32 plus 3 times 0.8288 and so on, right? We have all the numbers in the table, so just multiply these and then sum them together. You should get 0.25104. And then next up we need to find the variance of y. So there's a formula for variance related to the expected value. Let me see if I can find it here. It's right here. So it's the expected value of x squared minus the expected value of x all squared. Okay. Okay, so we need to calculate this, and then we know what this is from right here. That's 2.5. This literally means that instead of doing x or y times the probability, we do y squared times the probability, and then we sum these up. So then it's like 1 squared times 0.2 plus 2 squared times 0.32 plus 3 squared times 0.288 plus 4 squared times 0.1536 times 5 squared times 0.0384. Okay, and then I guess I should calculate this out. So 0.2 plus 4 times 0.32 plus 9 times 0.288 plus 16 times 0.1536 plus 25 times 0.0384. Alright, so then this is EY squared, and then from this we're going to subtract the expected value of y squared. So this right here is the expected value of y. So 2.5 1.5104 squared. Okay, there you go. So this is the variance, 1.18. Seven. Okay, make some more room. Then we use the expression in CII to find the value for P when these two are equal. CII? Oh, this thing, right? Okay. Okay, HI. So we want EX is equal to EY. So for EX, they said we're going to use 1 over P. And then for EY, we need... Wait, we know what EY is. They told us here, right? Okay. So this is just equal to 2.514. So, okay, yeah, this is only one mark. So P is 1 over 2.5104, whatever this is. Here we go. 398. Okay, next up. Find the variance of x given this value of p. So if this is the value of p, then, oh, here's the formula for variance that they told us. So we'll just use that instead of the long complicated one. Yeah, so like I said, like, paper theory is not that difficult. It's very guided. So 3.8. And then hence are determined which within reason which model provides a more consistent experience for the player with respect to boosted actions. So consistency has to do with how spread your data is. So we want a low spread, like a low standard deviation, or a low variance. So if we were to compare the two variances, this is 3.8. And if this is calculated correctly, this one is like 1 point something. So if you had to pick for consistency, then you would pick the variance. You would pick the second model here. So the second model says, right, on average, it takes 2.5 actions before you get boosted. And then it's quite consistent. The variance is 1. Whereas for this, right? For the same expected value, so the you're expecting about 2.5 actions before you get boosted in the first model, the variance for that is 3.8, which is like 3 times as much variance. So this is way less consistent. Okay, that was easy. 27 marks. Okay, that took me 2 more minutes than I should have, because I've been recording for 29 minutes. Okay, next one. This question investigates the ratio of lengths found from a line passing through the points of inflection of a curve, chordic curve. Like this, sure. Okay, this curve has points of inflection at B and C. The line passing through BC will intersect the curve again at a and d. So then we go through the steps. First is find the second derivative. Okay, easy peasy. Find the first derivative. Which means that the second one is 12x squared minus 18x. Boom, done. Okay, then we need to find the coordinates of B and C. So B and C, they said, were the inflection points. So the inflection points have a second derivative value of 0. So we just equate this to 0 and solve for x. And then they want the full coordinates, so then you'll have to also take those x values and substitute them back in for y. So the first thing is, okay, make this equal to 0. And then we can factor a 6x. And then that means that we have x is 0 and x is 3 over 2, like 1.5. And then, well, that's kind of obvious, that one's 0, and then this one right here is 1.5. Okay, and then we need to find their y values as well. So this one's easy. That one is 0, 0. And then for the second one, you can just plug it in to here. So I guess we'll do that. And here you go. As long as I put that in properly. 0.56 something. 25. Now, because this is an exact value, we can have more than 4 sig figs, I think. Usually IB says like you need to give 3 significant figures, but if it's an exact value, then maybe it'll be fine. Or you can just do all this work as a fraction and then deal with it as a fraction, but whatever. Then show that the equation of the line through BC is this. Okay, so this is a linear equation, and then all you need to find out is the slope. And we do have 2 coordinates, B and C, so you can literally just find the slope or the gradient using, like, you know, y2 minus y1. So I'm just gonna do C minus B, which is easy because B is just 0, 0. So essentially, this means that the slope is just the y-coordinate of C divided by the x-coordinate of C. So negative 5625 divided by 1.5. And that should probably give you the answer. Yeah. And then there's no b value, of course, because the y-intercept is on the origin. And then find correct to 3 decimal places the x-coordinate of d. So now we want to find d. And the way we can do that is we can literally, you have a graphing calculator. This is a graphing calculator allowed. So you can graph this, and then you can graph the line, and then you can just find their point of intersection. So for that, I'm going to use Desmos. Let me show it here. Okay, what was the function? X to the power of 4 minus 3, x to the power of 3 plus 3x, right? Okay. And then it's 375 for the linear one. So minus 0.375x. And then, like I said, all your GDCs can find a point of intersection right there. And then what do they want? The full coordinate or just the x coordinate? Just the x coordinate. So 2, 4, 2, 7. Okay. And then they generalize it. Find the x-coordinate of the 2 points of inflection in terms of m. Okay, so we're going to do the same thing, but generalized. First, we need to find the first derivative and then the second derivative. So first derivative is 4x cubed minus 3mx squared plus n. And then the second derivative is 12x squared minus 6m times x. Okay, and then it's the same process again, so you can make this equal to 0 to find the points of inflection. You factor out the 6x again, then you'll get 2x equals to m. And then you'll have your 2 points of inflection. So instead of 3 over 2, it's at m over 2. Which makes sense, right? Because this was like the same thing, but instead of m, we had 3. Okay. Then the line passing through BC intersects the curve again at A and D. Yeah, we know this. Okay. Write down the coordinates of B. B is always this one. It has to go through the origin. So easy peasy. And then find in terms of m and n the coordinates of C. C is the second point of inflection. So same thing, we're gonna plug in m over 2 into the function. And then, I guess, simplify it so it looks nice. Okay, so this is gonna be m over 4 over 16 minus m over 4 over 8 plus n times m over 2. And then, should I just keep going and make these look as nice as I can? So this is 2 over 16. This is 8 over 16. So this becomes what? 8nm minus m to the power of 4 over 16. This is the y value for an x value of m over 2. Something like that. Okay, then show that the equation of the line is this. Okay, so this is the same concept, right? We're just gonna take, this is c, and then we're gonna take c minus b, like the y values and then whatever. We're doing the same thing. We're finding the slope from C to B, but B is the origin. Okay, so then all I'm gonna do is... I don't know where I'm gonna write this. I'm gonna write it here. Okay, and then this divides pretty easily. 16 and 2 divide, so this is going to be 8. m will divide with these m's here. So you will get 8n minus m to the 3 over 8. And then if you just rearrange it, it'll turn into this. If you're not sure how to divide two fractions like the way I did, you just flip the second fraction over and multiply. You'll end up doing the same thing. But basically, if you have two fractions, like numerators divide with numerators, denominators also divide with denominators. Okay, done. Next up, show XA is this. Is it like this one? Oh no, I found XD last time. Oh sheesh, this one's 7 marks? Okay, this is the chunky one, the big one. Okay. So I need to find out XA, but we're gonna do a kind of similar thing. We need to find their intersection, of course, but of course we don't know m and n, so we can't graph it. But we're gonna equate the two equations, and then we'll just solve for x, and we'll see if that's possible. So the line is equal to the function, the quartic. I think this is it. Okay. Okay. And multiply this in, and then move everything over to this side. Actually, I don't think I need to multiply it in. Because this is just one term of x. Okay, and then these two are going to subtract together, add together. Like, you know, 2x minus 3x is negative 1x. And then this is 2 minus 3. We're going to do the same thing. So it's n minus... Oh, the n's cancel out. Okay, that's nice. Whatever. Let me just write this out in full. Okay, and there should be 4 solutions, right? X, A, B, C, D. Now, what's nice is that we already know B and C, so we can do a couple of things. First off, we're going to factor out the X. And this is xb, right? The solution to this equation. And then we also know that xc is a solution to this one. And then this was m over 2. So what we can do is, this is like polynomial division. We're going to divide out this factor so that we'll get a quadratic. And then we'll see if we can factor the quadratic, and then those would be XA and XD. So now we're gonna do a synthetic division. I think there's a 0, right? For x. Minus m over 3 to the power of 8. Wait, this is supposed to be 0, so I messed up my sign somewhere. This one goes over there. Oh, I forgot a minus in here. There's a minus in here, which means that this is a plus. 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 Anyways, I know I messed up because I already know m over 2 is a factor, so when I synthetic divide, I should have no remainder. This should have been a 0. Okay, so now I have x squared minus m over 2x minus m squared over 4. Okay. And then... okay, there's a root 5, which tells me... I think I need to use the quadratic formula on this next to find the two solutions that I'm missing, xa and xbd. So this is like, if we factor it out, like this. So now we use quadratic formula. So we have negative b plus or minus, and then I only need xa, and I don't need xd for this one either. So xa is the smallest x value, they tell you that. In other words, I don't need to really worry about the plus in the quadratic formula. I'm gonna save myself a tiny bit of time and just do minus square root of b squared minus 4 times a times c divided by 2a. Okay. And then, what the heck is this? So this is plus 4m, and then I'm not going to reduce it or cancel it with this 4, so that, because these are the same denominator, this is going to be 5m squared over 4 over 2, and then I can do m over 2 minus root 5 m over 2 over 2. Okay, and then we're basically done, right? And then this is essentially the same as m over 4. We divide each thing by 2. Root 5 over 4m. So that's xa. Yeah. Okay, and then we're almost done. Hence find the exact value of xb minus xa over xc minus xb. What are they even asking you to find here? Oh, this horizontal distance compared to this horizontal distance, right? Yeah, whatever. BACB. BACB. Okay, we know all of these values. 0 minus m over 4 plus root 5 over 4m over c was, what was xc? That was m over 2, right? Minus 0. Okay. Oh, this is nice. M's divide. 2 divides. So you get a constant? So I guess this ratio of lengths, which is what the question was asking you to explore, is always going to be a constant regardless of your coefficients for m and n. And then is this number the same as... No, we never found another ratio before. Huh. Okay, there you go. We're done. Easy peasy. This is why I like paper 3s. And then I guess I will do paper 2. I don't know when, to be honest. I hate paper 2s so much. Even the calculator work for this one, ugh, I didn't like pulling up the distribution, the binomial distribution function. And that was already simple enough to do. Well, let me know if I did something wrong. See you guys later.